Hello friends, welcome to engineering tutorial. So here we are with another question. So it has been asked to find the electric field at the center of a hemispherical surface having uniform surface charge density sigma. Okay, so this is the question. For to save time, I've already drawn the diagram. ABC is the hemispherical surface. It is in 2D, actually it is a 3D diagram where we have the whole surface. So for the entire hemispherical surface, we have to find the net electric field at the center O. That is our objective. So if you remember, like we did in the previous question, the semicircular arc, we converted the whole circumference of the semicircular arc into small elements, length elements dl. Okay, because there the linear charge density was given. Here the surface charge density is given. So what is surface charge density? Suppose we have a surface, okay, we have a surface, let's say of this kind. We have been given that the total area of this surface is A and the total charge that is distributed uniformly over this area is Q. So the surface charge density is the total charge divided by the total area, charge per unit area, which is coulomb per meter square. So what we'll do, we'll divide the surface into small number of areas for calculating the total one, and then we'll sum it together. We pick one small unit element and we'll integrate it over to get the total surface charge, the electric field due to the entire thing. So that's what we are doing here. Here, for calculating the electric field due to the entire surface of the hemispherical surface, what we have done, we have taken a portion, okay, of this hemisphere, a ring-shaped portion, ring-shaped surface, PQRS. Okay, so the electric field intensity due to this ring, okay, so here let's say we pick two ends of the ring, the lower and upper end of the ring, and we connect it here, okay. From this point to this point and this point to this point, okay, we have connected it. Now here the radius of this surface, that is equal to A, that is equal to A. Let's use a different ink color. This radius is equal to A. Let this angle between these 2 points, which is subtended, is d theta. Let me write it here, okay. This angle is d theta, okay, and this angle is, let's say, theta, okay. So now let this resultant electric field due to this portion, this ring PQRS, that be this one, delta E vector, okay, this one, delta E vector, the left hand side portion, okay, the left hand portion of the ring I am talking about, the left hand portion of the ring. So here this angle will also be theta, okay. If you draw a vertical line here, this angle will also be theta. So again we can resolve this delta E vector into two parts. Okay, first delta E cos theta and this delta E sin theta, this two parts. So here, as it is a symmetrical structure, okay, it is a symmetrical structure, so exactly the opposite end on the right hand side, exactly on the opposite end, the right hand side, if we pick these 2 points Q and S, okay, if we pick these two ends Q and S, let the electric field intensity due to the right hand end of the ring, that be also delta E vector, because it is a symmetrical structure, surface charge distribution is same, sigma, radius is A, so that will also be delta E vector, and it will have two such components along the vertical and horizontal axis. In the vertical it will be same delta E cos theta, which will get added up, same delta E cos theta, but along the horizontal axis it will be delta E sin theta, but in the opposite direction to this. So this will get cancelled out. So for throughout this whole surface, if we convert this whole surface into n such rings, okay, n number of such rings, and we integrate it over, we will find that there will be vertical components, cos theta components, which will get added together in the vertical direction downwards, but the sin theta components will be of equal magnitude but in the opposite direction, and they will cancel each other out. So the only components which are contributing towards the electric field intensity here, they are delta E cos theta components. This. Okay, so now we have to make some calculations related to the ring shape structure. So here, this thickness of the ring for this PR, this one, this portion PR, we know that the length of a arc, the arc length, okay, let's say we have an arc like this, of this shape, of radius we have, let's say, A, and we have angle, central angle theta. The length of the arc A, it will be equal to A theta, okay, that is the formula of arc length. So here the length or the thickness of this ring PR, that will be equal to the central angle d theta multiplied with the radius of the hemisphere, which is A. So that is equal to A d theta, which is basically the thickness of the ring. This, then the surface area of the ring, okay, the surface area of this ring PQRS, that is equal to surface area of the ring PQRS, that is equal to circumference of the ring, okay, this is the ring shape structure we have taken, circumference of ring multiplied with thickness of the ring. So here, for calculating the surface area of this ring structure, let us determine the radius PM, okay, PM. So this is A radius, this is theta, so this will be basically A sin theta, A sin theta, okay, PM is equal to A sin theta. And the circumference of the ring, we know circumference of a circle is 2 pi r, so here it will be, circumference of the ring will be 2 pi multiplied with the radius of this ring shape structure, which is PM, 2 pi into PM, which is equal to 2 pi into A sin theta. Thickness of the ring we have already calculated, that is equal to a d theta. So it will be a d theta. So that will be equal to, finally, the surface area of the ring is equal to 2 pi a square sine theta d theta. That is the surface area of PQRS ring, this one. Okay, now the charge on this portion of the ring, charge on PQRS ring area, this highlighted portion PQRS ring area, is the surface charge density, which is given sigma surface charge density multiplied with ring area, which is equal to sigma multiplied with 2 pi a square sine theta d theta, which is equal to 2 pi sigma a square sine theta d theta. Okay, let this charge be q over this ring shape structure q PQRS. Okay, let's call it that. So here the electric field intensity delta E vector will be equal to because of this ring, okay, this ring PQRS will be equal to 1 by 4 pi epsilon 0 q PQRS, this ring shape structure, divided by a square, because the radius of the ring is a square. Okay, a square by a square. Okay, and the only contributing component here is delta E cos theta, because sin theta components are getting cancelled out. So we can write it as delta E cos theta is equal to 1 by 4 pi epsilon 0 QPRS is equal to 2 pi sigma a square sine theta d theta by a square. A square gets cancelled, so it is simply 1 by 4 pi epsilon 0 2 pi sigma sine theta d theta, this much. Now the net electric field intensity delta E is simply the summation of the cos theta component, or the integration of the cos theta component. Okay, the cos theta component. Now what will be the limit of such integration? See here, I have said from the start that we are dividing this whole semicircular region into two halves, left half, right half. For left half portion PR, this red delta E vector is the electric field component. When it goes to the right hand half side, QS, for the QS portion, the ring QS portion of the ring shape structure, the right half BOC, okay, BOC, when we consider the right half, the electric field component is in the purple color, delta E vector. Sin theta components gets cancelled out and we get the net resultant in the vertically downward direction. So we are picking this ring shape structure. In order to calculate the electric field intensity for this entire surface area, we have to convert this whole ring shape, this semicircular ring. Okay, I'm just demonstrating here what we are doing. We are converting this whole thing into n such small rings, and we are performing the integration. Now here we are considering both halves, left half and right half. So for each half, the limit of integration will be from this 0 to 90 degree or pi by 2. Okay, because we are considering only 1/2. Okay, this. So here the limit of integration, when we integrate it, okay, delta E, it will be integration of 1 by 4 pi epsilon 0 2 pi sigma sine theta d theta from 0 to pi by 2. So that will be equal to, so we'll bring sigma by 4 pi epsilon 0 outside, so it will be pi will get cancelled. We are only cancelling pi, sigma by 4 epsilon 0. Okay, so then it will be sigma by 4 epsilon 0. Okay, it will be sigma by 4 epsilon 0. Sigma by 4 epsilon 0, this will be 2 sine theta. Okay, one thing. So here we have missed one thing, that is, here we have to bring this cos theta component. Okay, here we have to bring another cos theta component because we have missed it here. Okay, delta E cos theta, this is delta E. Okay, we have put this, so here we'll have to add another cos theta d theta because the cos theta component is there, only contributing towards this. So it will be cos theta d theta. Okay, cos theta d theta. This is the expression of delta E. Okay, so here it will be cos theta d theta. Sin theta here will be cos theta d theta. Here I have missed, it's a mistake. Okay, so it will be cos theta d theta. So here also we have to add that. By mistake I have missed it. So these kind of mistakes can also happen, so please be careful. If you miss one component, it will be wrong. So 2 sin theta cos theta, it will be here 2 sin theta cos theta. So that will be equal to sigma by 4 epsilon 0 to pi by 2. This is sin 2 theta. So 2 sin theta into cos theta is 2 sin theta cos theta. Sin 2 theta is this much. So then it will be sigma by 4 epsilon 0, it will be minus cos 2 theta by 2 pi by 2 0. So that will be, bringing the 2 outside, sigma by 8 epsilon 0, that is equal to, if you also take the minus outside, it will be cos 2 pi by 2, that is cos pi, minus cos 2 0, that is cos 0, that is equal to minus sigma by 8 epsilon 0 to minus 1, which is equal to sigma by 4 epsilon 0. Yes, this is the net electric field intensity. So the net electric field intensity at the, okay, not this, total electric field intensity delta E is the only for the PQRS ring. For the total electric field intensity at center O is equal to sigma by 4 epsilon 0. This. So here again I want to just clarify. Here we miss the cos theta component. See, we have already mentioned that cos theta is the contributing component. Sin theta components are getting cancelled. We got delta E value as this 1 by 4 pi epsilon 0 QPRS by A square. We substituted the value of QPRS, which is this 2 pi sigma A square sin theta d theta. But that is delta E. delta E cos theta. For cos theta we have to add another cos theta here, which we missed. That was the whole point. Okay, we missed this cos theta part. We are only doing delta E because we proved it here that only contributing factor component to this electric field intensity is the delta E cos theta. So we added that cos theta here and we solved it. Okay, so again it was a mistake that I missed that cos theta. Please be careful, it can happen when you derive such long expressions. You can miss some important crucial steps and that will lead to wrong expression. Okay, so this is the solution. The electric field at the center of a hemispherical surface having surface charge density sigma. Okay, so friends, I hope you like this video and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.